Good morning to all of you.
Good morning, sir.
Good morning, sir.
Good morning.
Good morning, sir.
Good morning. So, is my screen visible?
Yes, sir.
Yes, sir. It is visible.
Are there any questions, doubts? Anybody? Any question? Any doubt?
Sir, in the previous day, we are talking about bicubic element, that is N1 equals to H1 H2, like
Yeah.
this. But I can't remember the sequence. Like N1 is H1 H1, N5 is
So
H3
the
H1.
logic, see, the logic is when you are defining that, so N1 is corresponding to W degree of freedom of the first node. First node means along the x direction it is first, along y direction also it is first, and W. So from the Hermite interpolation we take h1 along x and also h1 along y. Then when we define n2 is corresponding to del w by del x degree of freedom at first node of the element. So again, along x also in corresponding one dimensional Hermite elements if we see. So along x direction it is first node, along y direction also it is first node, but along x it is derivative with respect to x. So that is why h2, because in the corresponding one dimensional model with derivative at first node, h2 is the shape function which goes. So let me open and then I will explain. Yeah, I think that is better. So if uh, so yeah, here if you see corresponding one dimensional Euler-Bernoulli beam element, so W is H1 W1 plus H2 del W by del X at 1 plus H3 W2 plus H4 into del W by del X at 2. So here you see the H1 and H2 are corresponding to first node. H1 goes with W, H2 goes with derivative of W. H3 and H4 are corresponding to second node. H3 goes with W and H4 goes with derivative of W. So when you define the N1, so N1 is a first node along X, also first node along Y, and it is W, so no derivative. So H1 into H1. When you go for N2, is the shape function corresponding to del W by del X degree of freedom at node 1. So now its derivative with respect to X. So it would be corresponding to H2, because H2 shape function goes with derivative. So that is why this is H2 into H1 H1 for N2. N3 is the shape function at node 1 corresponding to del W by del X degree of del W by del Y degree of freedom. So again it's first node along X and Y, but the derivative is with respect to Y. So X direction H1 and Y direction it is H2. When you go for N4 is the shape function at node 1 corresponding to del 2W by del X del Y degree of freedom. So derivative with respect to X also, derivative with respect to Y also. So that is why you have here H2 into H2. And then you go to N5, which is corresponding to W of node 2. So now along X it is node 2, along Y it is still the Y equal to 0. That means the starting node. So now along, because at N5 corresponding to W at node 2, and W at node 2 along X will correspond to H3 shape function. So H3 into H1, and then M6 is del W by del X. So H4 into H1. So that is how the logic is. Is that clear?
Yes, sir.
Okay.
Hello, sir.
So yeah,
Sir, in MATLAB program,
yeah.
we have to means calculate the N1 N2 all in paper, then put in MATLAB, or in MATLAB coding only we have to calculate N1 N2 all the step functions.
Yeah, I see. For the problem which I have given is for the element with 3 degrees of freedom at each node. No, so you have to calculate shape functions also in MATLAB. You can use symbolics and symbolic manipulation and can calculate the shape functions. And symbolic shape functions can be differentiated with respect to x and y.
Okay, okay.
हेलो हाँ guys, ये मेरी क्लास चल रही है. Yeah, so you have to do these calculation in MATLAB itself.
Okay, okay,
Okay.
okay, sir.
Are there
Hello,
any
sir.
other question, doubt?
Hello, sir.
Yeah.
Sir, when we calculate for fourth node, then we need to consider that fourth node as a first and one as a second,
Yeah,
or
along
what?
x it is first, along x it is first, and along y it is second.
That means, sir, we consider that first and second with respect to origin.
Yeah, with respect to origin, yes.
Okay, sir. Okay. Thank you.
Are there any other questions, doubts? Okay, so then let me go to the next one.
Hello, sir.
Yeah.
Sir, if plate is fixed in both the end, then if you apply transverse load, then in that case sigma zz will not be means its value should be comparable. Means its value will affect, na, sir. If the plate
Sigma,
is
you are saying sigma zz. We are
uh,
taking sigma zz approximately 0 because it
then
would be much smaller compared to sigma xx and sigma yy and tau xy. So
sir,
that is,
if the plate is fixed both the end,
yeah, even if it is fixed, whatever is the whatever are the boundary conditions, sigma x zz would be much smaller compared to sigma xx, sigma yy and tau xy. So that is why we take the condition sigma zz equal to 0 for writing the relationship between stresses and strains.
okay.
Okay, so then let me start. So is my screen visible? No, sir. Okay.
No, sir. Yes,
Yeah.
sir.
So
Now it is visible.
is it visible? Screen is visible. Is the screen visible? Visible? Hello. Yeah, I
Yes, sir.
think
Now it is
someone.
visible.
Okay.
Yes, sir.
Yeah, please mute yourself. I think someone is creating noise. So we were discussing the first order shear deformation plate theory based finite limits. First order shear deformation plate theory based elements. So I had in the last class, I had written this, I think the integral functional. So I had said I, the integral functional is half integration over volume and then sigma transpose into epsilon. These we had defined plus half integration over volume, shear correction factor Ks, and then tau transpose into gamma dV minus the integration over area W transpose into QdA, and minus we had the boundary integral, so we had W transpose into Qn, plus we had theta n transpose into mnn plus theta s transpose into mns ds. So I had defined all these quantities through a figure. So this is where we were in the last class, and I had said that mn. So if you have a, yeah, if you talk of any boundary, so boundary normal is n and tangent is s. So about this s, we have this mnn, and in the same, about the same direction we have theta n. And we had about s, we had about no, this n, we had m ns, and theta is about the same. And then we had, I had also shown that in the z direction we have this qn and w. So based on that, this is how the boundary terms were written. So now we write, now find, if you look at the epsilon strain, which is this epsilon xx, epsilon yy, and gamma xy in plane shear, normal and shear strains. So these are written in terms of z. So we want to separate out the z. So we can write this as a matrix in z, and then curvature tensor. So del theta x by del x, del theta y by del y, and del theta x by del y plus del theta y by del x. So this is epsilon xx is del into z into del theta x by del x. So that would be z into 0 0, z and 0 0. Epsilon yy is z into del theta y by del y, so that would be 0 z 0, and then gamma xy is 0 0 and z into this term. So we can say this as z matrix, and this has the curvature tensor. So this is z and this is the curvature. So this kappa we call as curvature tensor, written in the vector form. All the elements are put into a vector form. So this is curvature tensor. Similarly, if you look at the transverse shear strain vector gamma, so that is consisting of gamma xz and gamma yz, transverse shear strains. So this is simply theta x plus del w by del x and theta y plus del w by del y. So now if you look at this integral functional I, we substitute these expressions for epsilon gamma in the integral functional. So we can write, split the volume integral into area and through the thickness integration. So we can say the integration over area, integration over thickness minus h by 2 to plus h by 2. And then we have sigma transpose, like here we have now this sigma transpose into epsilon. Sigma is c into epsilon, so sigma transpose would be epsilon transpose into c transpose, and c is symmetric, so it would be equal to c. And then epsilon transpose would be kappa transpose into z. So we can write that as kappa transpose into z transpose into c, and then into z, and then again epsilon, which is z into kappa. So z into kappa dz dA, and then the transverse shear strain energy term again would be half integration over area, integration through the thickness, and that can be written as, now tau is cs into gamma, is transpose would be gamma transpose into cs. Cs is symmetric, so we can write that as gamma transpose into cs into gamma into dz dA, and then the other terms are written as it is. So minus integration over area W transpose into QdA and minus integration over boundary. So here of course we have this Ks, shear correction factor, Ks is a shear correction factor, and this integral is W transpose into Qn plus theta n transpose, theta n transpose mnn plus theta s transpose mns ds. So now if you look at this integration of z transpose c into z through the thickness will be, I know you can see it would be in terms of es cube upon 12 1 minus nu square and nu into eh cube 12 1 1 minus nu square. So those kind of integrals you will get. So we can write this integral functional I as half and then integration over area, and then we have this kappa transpose into this matrix we define as D matrix. So D into kappa dA and plus half integration over area, and let us absorb the ks in the know that matrix inside. So I will define that. So this can be written as gamma transpose into E into gamma dA into gamma dA. So and then we will have the other terms, that is minus integration over area W transpose into QdA minus integration over volume W transpose into Qn plus theta n transpose into Mnn plus theta s transpose into Mns ds. So this will be by the integral functional. Now where D, where matrix D is this integration through the thickness minus h by 2 to plus h by 2 z transpose into C into z dz. So this will be, you can look at, the it would be in terms of es cube upon 12 1 minus nu square and so on. So similarly here the matrix E which I have defined here, the matrix is minus h by 2 to plus h by 2 the shear correction factor Ks into Cs. So it would be Cs dz. So this integration will give you the matrix E. So yeah, this is finally the integral functional we have got over here, and you can now multiply and look at these integrations. So now let us see, although most commonly what we use is the plate bending element for the first order shear deformation theory, are most commonly used elements are 4-noded isoparametric element and 8-noded isoparametric element. Sometimes people do use 9-noded isoparametric element. So these are the most commonly used elements, but let us look at the possible elements, what all we can have. So now when we talk of the possible finite elements, what are the possible finite elements? So now whatever elements which develop formulate, we have to have, because the primary variables in this problem the are w, theta x and theta y, because they define the three displacements u, v and w. So u is defined in terms of theta x, v is defined in terms of theta y and w. So we have w, theta x and theta y as the primary variables, are the geometric quantities. So these should be continuous across the element boundaries for the compatible elements. And see, when we are because classical plate bending element was involving derivatives of w, so we had talked about the compatible and incompatible elements, but here no, we it is possible to formulate the compatible elements when the derivatives of the variables are not involved. So we talk of only the compatible elements. So for possible elements, W theta x theta y should be continuous across the element boundaries. And this implies, so for this, no, the first requirement is that these should be nodal degrees of freedom. That means first requirement. And then of course we have to ensure that the compatibility conditions are satisfied. So these should be, that is, these means W theta x theta y should be nodal degrees of freedom. So now we have 3 degrees of freedom at each node, W theta x and theta y, and for the, depending on the elements, we will have the elemental degrees of freedom. So the simplest thing we can think of is a 3-noded triangular element. 3-noded triangular element, and that element would be basically, so if you look at triangular element and say the coordinates are xy here, this is the first node, this is the second node, and let us say this is the third node, and the coordinates here are x1 y1, x2 y2, and here x3 y3. The degrees of freedom, because we said no, the primary variables should be degrees of freedom at the nodes, so we will have w1 theta x1 theta y1. Similarly at this node we will have w2 theta x2 theta y2. At node 3 we will have w3 theta x3 theta y3. So these would be degrees of freedom. So at nodes, because these are the primary variables and this would be degrees of freedom at the nodes, and let us say we have any point P and its coordinates are x and y. So now for this, because if we look at the integral functional, so we require first derivative of all the variables w theta x and theta y. So whatever we assume, it should be differentiable at least once, and also now we have corresponding to each variable, that is w theta x or theta y, there are 3 degrees of freedom over the entire element, so we can have 3 constants in the approximate solution. So we can assume w as a0 plus a1x plus a2y, and so it is differentiable once with respect to x and y. It is a complete polynomial, it is geometrically invariant, and we have the a0 a1 a2 can be expressed in terms of values of w at node 1 2 and 3. So we need to of course check, only thing is the compatibility, so I will discuss that. Theta x similarly can be written as b0 plus b1x plus b2y, and theta y can be written as c0 plus c1x plus c2y. So, and then of course now you can express a0 a1 a2 in terms of w1 w2 w3, and similarly b0 b1 b2 can be expressed in terms of theta x1 theta x2 theta x3 and so on. And then you can write these in terms of shape functions, what are, and those shape functions turn out to be no area coordinates, so we can write it, these basically in terms of area coordinates. So now let us check the compatibility. So if you remember in the plane stress strain elements, I have talked about the compatibility. So the same logic holds here. So let us say that we have a rectangular geometry and we discretize that into 2 triangles. So this is element 1, this is element 2, and these are the nodes. And say this is the node 1, 2, 3, and 4. So if you look at boundary 1, 4 is a common boundary. Boundary 1 4 is common boundary between element 1 and 2. At node 1 and 4 we will have the common degrees of freedom in no element 1 as well as element 2. W theta x and theta y would be common at node 1 for both the elements, element 1 and element 2. Similarly at node 4, W theta x and theta y degrees of freedom would be common to element 1 and as well as element 2. And now what would be the in between variation? So equation of line 1 4 is going to be like y is equal to mx plus c. So if you substitute here in these expressions, you will find that these are going to be linear in x. So if it is linear in x, So we have value of W at node 1, value of W at node 4, and in between it is a straight line. So that would be unique because value of W at node 1 and 4 is same for both elements 1 and 2. So that means this element would be a compatible element. So it would be a compatible or conforming element. The logic is similar what I had discussed in detail for the plane stress, plane strain elements. So same way, you can put that logic. So the conclusion is that the this triangular element with three terms in the approximate solution in each variable w theta x and theta y, the element is a compatible element. Now we express these unknown constants a0, a1, a2, b0, b1, b2, c0, c1, c2 in terms of degrees of freedom. So finally, the approximations for w theta x and theta y come out to be in terms of area coordinates. So this also we have what are known as the area coordinates, and the area coordinates are defined now in this triangle. So if you look at this triangle over here, so L1 is the area coordinate corresponding to node 1. So that is the ratio of area of the triangle P23 upon area of the entire triangle 123. L2 is this area coordinate corresponding to node 2. So that is area of triangle P31 divided by area of the triangle 123, and area coordinate L3 is corresponding to node number 3. So that is area of the triangle P12 divided by area of the triangle 123. So this is how you define the area coordinates. मेरी क्लास चल रही है, मैंने सर को ईमेल में लिख दिया था कि ठीक है. हाँ, हेलो. Yeah, is there am I audible?
Yes, sir. Can you please explain again area coordinates? How P23? What is?
Yeah, so the area coordinates is, this is the triangle, this is xy, these are the nodes, this is 1, this is 2, this is node 3, and P is any point inside the triangle with the coordinates as xy. So when we define the area coordinate L1, so that is corresponding to node 1. So it is the ratio of the triangle, no excluding node 1. So when exclude node 1, it would be area of the triangle P23. That is basically area of this triangle P23 divided by area of the entire triangle. When you go to node L2, which is the area coordinate corresponding to node 2, so we choose a triangle which is excluding node 2. So that would be P31, area of the triangle P31. So that is this triangle from here to here, this triangle P31 divided by area of the entire triangle 1, 2, 3. And then L3 is corresponding to node 3. So that is area of the triangle excluding node 3. So when you exclude node 3, you take P1 and 2. So P area of the triangle P12 divided by area of the entire triangle 1, 2, 3. So that is how you define the area coordinates.
Hello,
So
sir.
P is a variable xy coordinate inside the element. 1, 2, 3 are the coordinates of the nodes 1, 2, and 3. x1, y1, x2, y2, x3, y3.
Hello, sir.
Yeah.
L1 coordinate should be in x and y, na? Two coordinates should be there.
No,
Then it will be.
yeah, it would be in terms of x and y because area of the triangle P23 will be in terms of x and y.
Yes, sir. Okay. Yes, sir. Yes.
Yeah, area of the all the P23, P1, P31, P12 will be in terms of x and y. So L1, L2, L3, all three will be functions of x and y, and they will also involve the coordinates of nodes 1, 2, and 3, x1, y1, x2, y2, x3, y3.
Yes, yes. Okay.
Okay. Yeah, is it clear? Okay, so let me continue then. So now if you write the interpolation for all the variables, so w, theta x and theta y, these can be written in terms of area, and the property of these area coordinates is, if you look at L1, So L1 would be unity at node 1 and would be 0 at 2 and 3. So when we evaluate L1 at node 1, so that means P will be 1 in, no 1. So it would be area of 1, 2, 3 divided by area of 1, 2, 3. So it would be unity. And when you evaluate L1 at node 2, so then P is coinciding with node 2. So area P23 will be a straight line. So area would be 0. So L1 at node 2 would be 0, and similarly L1 at node 3 will also be 0. Similarly, when you look at L2, L2 would be unity at node 1, 0 at node 3 and 1. L3 would be unity at node 3 and would be 0 at node 1 and 2. So that's the property of these area coordinates. So these are, yes. So then you can write these in terms of these area coordinates W and all the terms. So degrees of freedom vector would be W1 theta x1 theta y1, W2 theta x2 theta y2, W3 theta x3 theta y3, and then W would be L1 W1 plus L2 W2 plus L3 W3. So that would be L1 0 0, L2 0 0, L3 0 0. And theta x would be L1 theta x1 plus L2 theta x2 plus L3 theta x3. So it would be 0 L1 0, 0 L2 0, L3 0. And theta y would be 0 0 L1, 0 0 L2, 0 0 L3. So this is the interpolation of all the three field variables, and this you can say as matrix H. So this is H
Excuse
into
me, sir.
vector of, yeah, vector of
Sir,
elemental degree. Yes.
sir, in spite of having that XY coordinate, that is the global coordinate system, why we are jumping to the area coordinate? Like, what is the its special advantage we are getting out of it?
No, see what you are going to do is you have to express no this small a0 a1 a2 in terms of w1 w2 and w3. And when you collect the coefficients of w1 w2 and w3, so whatever say functions you get, they turn out to be these area coordinates l1 l2 l3. So that is why we use this. So these are nothing but actually safe functions. For the 300 triangular element, L1, L2, L3 are safe functions. So in this approximation, W is equal to A0 plus A1x plus A2y. We write W1 is equal to A0 plus A1x1 plus A2y1. W2 would be equal to A0 plus A1x2 plus A2y2. W3 will be A0 plus A1x2 plus A1x3 plus A2y3. And solve for A0, A1, A2 in terms of W1, W2, W3 and put back here. And then whatever say functions you get, they turn out to be these area coordinates. So that is why I'm writing, no, and these turn out to be ratio of these areas. So that is why I'm writing it in terms of area coordinates.
Okay, so that safe function in terms of the area coordinate will be a function
Yeah.
of global coordinate system, that is XY.
Yeah, that's right. So, for example, now if you look at the areas, so if I look at the area of triangle P23, so area of the triangle P23 can be written as it can be written in terms of the determinants of determinant 3 by 3 determinants. So it would be half 1 per P means the coordinates of P are x and y, and then node 2, so 1 x2 y2 and 1 then x3 y3, this determinant. And now when you open this determinant, you will have no it in terms of x and y. Similarly, area of the triangle 1 2 3 would be half, and determinant 1 x1 y1, 1 x2 y2, 1 x3 y3. And you open this determinant, so this is going to be directly the area. Let us say the area of the triangle A. So you can say the L1 would be 1 upon 2a into this determinant. And this determinant you can open in terms of the first row. So it would be having some constant term and the x and y terms. So like that other
Yes.
area coordinates.
Thank you, sir.
Yeah. Yeah. So
Sir, L3 is dependent on L1 and L2.
yeah, sum of these three is equal to unity. Yes. L1 plus L2 plus L3 is going to be unity. So you can write one in terms of the other two. That is true. Any other doubt? So I of course I expected that this you would have done in the basic FEM course, because in the plane stress plane strain elements one talks about the constant strain triangle CST element. So there we talk about these area coordinates, and but I have given you some background anyway. So similarly now in the approximations we also need W separately in the potential of externally applied load. So you can write W simply as L100, L200, L300 into DE, vector of elemental degrees of freedom. D we have already defined. So this you can say HW into DE. And similarly for theta n and theta s, so theta n and theta s would be written in terms of theta n would be equal to nx into theta x plus ny into theta y. And similarly you can write theta s in terms of theta x and theta y. So their interpolations can also be written in a similar manner. Now we need the curvature tensor in the integral functional. So the curvature tensor kappa will be equal to, we have already said that it is del theta x by del x, del theta y by del y, del theta x by del y plus del theta y by del x. So this will be equal to this side you have d. I am not writing so the same d. So del theta x by del x is going to be 0 del no. So I will not define all the elements. Now you know how to do it. So 0 del L1 by del x, 0, and then 0 del L2 by del x, 0 0 del L3 by del x, and 0. Then theta y would be 0 0 del L1 by del y, 0 0 del L2 by del y, and then 0 0 del L3 by del y. And this will be 0 del L1 by del y, del L1 by del x, because it is involving both theta x and theta y. 0 del L2 by del y, del L2 by del x. 0 del L3 by del y, del L3 by del x. So this is the curvature, and let us call this matrix as B. So this will become B into DE, and this D is already there. So this is a curvature. Similarly, if you want to define this gamma, now the transverse shear strain terms. So gamma is nothing but, we have said it is theta x plus del w by del x and theta y plus del w by del y. We have already defined this. So this can be written as, again in terms of dE. So d we have, so this is del w by del x. So we will have del L1 by del x, and then plus theta x is there. So here L1 will come 0, that is theta y is not there. Del 2 by del x, L2 0, del L3 by del x, L3 and 0. And similarly this will be del L1 by del y, 0 L1, and then del L2 by del y, 0 L2, del L3 by del y, 0 L3. So this is for defining the transverse shear strains. So then this is well, let us say call it as matrix BS for the transverse shear strain into DE. So this is your BS matrix. So now you substitute all of these in the integral functional, and then for equilibrium delta of I equal to 0 for any arbitrary delta d, you get the element level governing equation. So those steps are same for any element you develop from the integral functional. So I am not writing those steps. So let me just write the element level governing equation. So the element level governing equation is going to be the form of the equation is same, that is element level stiffness matrix Ke into the vector of elemental degrees of freedom De is equal to a fixed external, that is distributed load Q, and the boundary forces in the element. So that I am calling as F internal for the element. So this will be the element level governing equation, where the element level stiffness matrix Ke in this case is now going to be the integration over area of the element, and it would be B transpose into D into B into dA plus the integration over area Bs transpose into E into Bs into dA. So this is your stiffness matrix, and the external load vector F external for the element would be integration over area again. It would be HW transpose into QdA. Because of the distributed load Q, this is the the external force, and F internal for the element would be integration over the boundary, and then you have HW transpose into Q, and plus we will have interpolation of theta n. So let us say that is S theta n transpose into mn, plus you will have interpolation of theta s. So let us say that is S theta s transpose into mns. You will have into ds. So this is the internal load vector. So finally, this is what the element level governing equation is there. And when you are solving problems, you have to discretize the whole domain into a number of elements, and then assemble all the elements together, get the global stiffness matrix, global load vector, then impose the boundary condition and solve. So that is similar to the one problem I had demonstrated in the 1D case. So that part is similar, and of course you have to because these problems are involved, so you have to do all these things through a code, say MATLAB, Fortran, C, whatever you prefer to use. So this is a triangular element, and this is how you develop the entire thing. And then next is, let us in the physical coordinate itself, if we talk of the quadrilateral element. So in the physical coordinates, so similar to plane stress, plane strain problem I was talking about. So if you take a
Sir,
quadrilateral element, yes,
sir, one question. Like,
yeah,
since these are like widely used, whatever you are teaching us, so are
yeah.
there any code repository for these, like already available codes?
Is in some books you can actually find these codes, but whatever assignment I am giving, you have to develop your own. But there are, you can find in some books, like for example, yeah. But of course, the uh, I don't know any repository where you can find all of these. But some books you do find the some part of these codes you can find in those books.
Okay, sir.
But I expect you to develop your own code through the assignments.
Yes, sir. I was not asking what the assignment is like,
Yeah,
because like you were telling that like suppose area coordinate and other things, they are already developed.
yeah, yeah.
So that's why I was asking,
See,
like sometimes if we are stuck, we can refer those.
yeah, so repository, I don't know whether any repository is there, but in the books you can find a part of these codes you can find in the books.
Okay, sir.
Yeah,
Hello, sir.
yeah.
Sir, could you please re-explain that gamma matrix, how it came BS into D?
Okay, so see this gamma we have defined. So yeah, gamma, it is consisting of gamma xz and gamma yz. Gamma xz is theta x plus del w by del x, and gamma yz is theta y plus del w by del y. So this we had seen in the last derivation in the last class, right? So now if you look at this is theta x plus del w by del x, and theta x is no, your theta x is L1 theta x1 plus L2 theta x2 plus L3 theta x3, and plus del w by del x is del L1 by del x into W1 plus del L2 by del x into W2 plus del L3 by del x into W3. So the same thing is written here. No, your If you look at these del L1 by del X, del L2 by del X, and del L3 by del X are going with W. So when you multiply this row with DE, and DE is defined over here, if you see this W1 theta x1 theta y1, W2 theta x2 theta y2, W3 theta x3 theta y3. So these are defined here. So when you look at this multiplication, it will give you finally when you multiply say the first row with vector DE, you will exactly get this theta x plus del W by del X. So how I wrote here is because it involves del W by del X. W is coming in the first location in the D, fourth location in the D, and the seventh location in DE. So there we have this del L1 by del X, del L2 by del X, del L3 by del X. हेलो, अभी क्लास ही चल रही है. So so I am writing del L1 by del X, del L2 by del X, and del L3 by del X at locations 1, 4, and 7, and then theta x is there. Theta x is there as a in D. If you look at the second degree of freedom, and then it is fifth degree of freedom, and then it is eighth degree of freedom. So in those locations I am putting L1 so that when you multiply you exactly get this theta x plus del W by del X. Is that clear?
Yes, sir. Yes. Thank you.
No. Okay. So then I was talking about this quadrilateral element. So let us say we take a four noded quadrilateral element and arbitrary quadrilateral. If you take a rectangular element, you can satisfy the compatibility condition. But if we take a arbitrary quadrilateral, say nodes 1, 2, 3, and 4, and the coordinates are no x and y, and at each node of course we have the degrees of freedom are same w1, so the coordinates of this node are x1 y1, and similarly for the other nodes, and the degrees of freedom are w1 theta x1 theta y1, and similarly for other nodes. So in this case you will see that we will have four no degrees of freedom corresponding to each variable, that is 4 w's, w1, w2, w3, w4, similarly in theta x, theta y. So we will assume an approximate solution involving four terms. So we will get a0 plus a1x plus a2y plus a3xy. Similarly theta x you will take as b0 plus b1x plus b2y plus b3xy, and theta y you will take it as c0 plus c1x plus c2y plus c3xy. So now when you check the compatibility, so similar to know what we discussed already. So let us say we have some domain and we discretize this into a certain number of elements like this. So these are the nodes. Elements are 1, 2, 3, and 4 quadrilateral elements. You take any edge. Let us say if you take AB, AB is equal to AB will be y equal to mx plus c, and if you put here in this expression it will become quadratic in x. Since there are only two values common between element 1 and 3 at node A and B, so element 1 will give a different variation of W along line AB, element 3 will give a different variation of W along line AB, so it would be incompatible element. So the logic is similar to what we have already discussed, so this would be incompatible. The triangular element is compatible. If you take a rectangular element, that will also be compatible. But if you take four noded quadrilateral element, similarly if you go for eight noded arbitrary quadrilateral element, that will also be incompatible. So these elements would be incompatible. So then again to develop the compatible elements, we go for the isoparametric formulation. So we talk of the four noded, let us say four noded isoparametric element. So here what you do, as I discussed in the, if you remember in the plane stress, plane strain problem, I have explained you this. So be in the xy coordinate, that element is arbitrary quadrilateral. and this is mapped to a square in the natural coordinate space. So these are nodes 1, 2, 3, and 4. We know the coordinates are x1, y1, x2, y2, x3, y3, and x4, y4. So these are the coordinates. Similarly, we'll have degrees of freedom, w, theta x, and theta y at each node. So this is mapped to the square in the natural coordinate space, xi and eta. The nodes are 1, so node 1 in the physical coordinate space corresponds to node 1 in the natural coordinate space. Similarly, 2, 3, and 4. And the coordinates of these nodes are -1, -1, 1, and -1. This is 1 and 1, and this is -1 and 1. So again, now you interpolate all the w, theta x, and theta y. So you will basically write w is equal to a0. Now the interpolation is in terms of the natural coordinates. So w will be a0 plus a1 xi plus a2 eta plus a3 xi eta. And similarly, no, for theta x, say b0 plus b1 xi plus b2 eta plus b3 xi eta. So similarly, theta y, c0 plus c1 xi plus c2 eta plus c3 xi eta. And we also need the relationship between x and y. So you also interpolate x and y. X would be, say, d0 plus d1 xi plus d2 eta plus d3 xi eta, and y will be e0 plus e1 xi plus e2 eta plus e3 xi. So you write these all, the a0, a1, a2, a3, all these constant in terms of the values of w at node 1, 2, and 3, and you get the shape functions. So finally, now we have already discussed the entire steps. So finally, now you can write w is equal to summation over I going from 1 to 4 ni wi, where ni's are shape function and wi is the value of w at node 1 and ith node. Similarly, now you can write theta x as ni theta xi, theta y as summation ni theta yi, and x can be written as summation ni xi, and y can be written as summation ni yi. So the summation is from I going from 1 to 4. And we have also actually already discussed how to write the shape functions. So the shape functions you already know, we have written already. N1 for the 4 noded isoparametric element, the shape function N1 is 1 by 4, 1 minus xi, 1 minus eta. N2 is 1 by 4, 1 plus xi, 1 minus eta. And N3 is 1 by 4, 1 plus xi, 1 plus eta. And N4 is 1 by 4, 1 minus xi, 1 plus eta. So these are your shape functions. I have also, so once you have this idea, the rest of the derivation is similar. Any element you want to develop, the derivations are going to be actually similar. So now if you remember, I have also introduced the concept of Jacobian matrix while discussing the plane stress, plane strain elements. So we had said because for defining the curvature tensor and the shear strain tensor, we need the derivatives of shape functions with respect to x and y. The shape functions are explicitly written in terms of xi and eta, so we can get their derivatives directly with respect to xi and eta, and then we have to write the derivatives of this shape function with respect to x and y. So we use the concept of Jacobian matrix. So the logic how we arrive at that I had already discussed. So the concept of Jacobian matrix, in that del by del xi and del by del eta, these two operators are related to del x by del xi, del y by del xi, del x by del eta, del y by del eta into del by del x, del by del y, these operators. So this we have already talked about, and this we call as the Jacobian matrix. And when you take the inverse of this relationship, so you write inverse relation So when you write the inverse relation, you write del these operators del by del x, del by del y as j inverse into del by del xi, del by del eta. So now you will know x and y also in terms of xi and eta through these interpolations. Now through these interpolation, this interpolation and this interpolation, x and y are expressed in terms of xi and eta. So you can directly get their derivatives with respect to xi and eta. And once you have those derivatives, you put into this, you get the Jacobian matrix, and then you can find out its inverse. So now you can write, let us say the inverse is J11 star, J12 star, J21 star, J22 star. These are the inverse of this 2 by 2 Jacobian matrix, del by del xi and del by del eta. So then now you need the derivatives of shape functions with respect to x and y. So if you take the any ith shape function, so del ni by del x would be J11 star into del ni by del xi, because it is del by del x, and del by del x is J11 star del by del xi plus J12 star del by del eta from this relationship. So when you operate it on ni, it would be J11 star del ni by del xi plus J12 star into del ni by del eta. And similarly the del ni by del y, these are the derivatives which we need in the integral functional. So this would be J21 star del ni by del xi plus J22 star into del ni by del eta. And you will notice that no, if the element is a rectangle in the physical coordinate space, then Jacobian will be constant with only non-zero diagonal elements J11 and J22. J12 and J21 would be actually zero for a element which is a rectangle in the physical coordinate space, that is in xy coordinate space. But if it is arbitrary quadrilateral in the physical coordinate space, then you will find J would be function of xi and eta, and all the elements would be non-zero for the arbitrary quadrilateral. So now once we have defined all this, so we need to write the interpolation for the curvature tensor. We need to write the interpolation for the transverse shear strain tensor, and then we develop the element level governing equations. So no, that means when you look at the curvature tensor, so you will have that kappa. The definition is same what we discussed in the triangular element. So that is this curvature tensor is del theta x by del x, del theta y by del y, and del theta x by del y plus del theta y by del x. So logic is same way now you define the B matrix. I will write only few elements, and now you can do yourself. And into the D, and the D in this case has, now you know, the vector of elemental degrees of freedom, DE is going to be, at each node we have 3 degrees of freedom. So D would be a vector of 3 into 4, 12. So D is going to be a 12 by 1 vector, and this would be 3 by 12. And now no, del theta x by del x. So in the degree of freedom vector, first we have w, then theta x, and then theta y. So we will write that as 0. We will write that as 0, then del n1 by del x, and that is, so that we get del theta x by del x is going to be del n1 by del x into theta x1 plus del n2 by del x into theta x2 plus del n3 by del x into theta x3 plus del n4 by del x into theta x4. So that is how you are writing these elements. So these elements you are writing at second location, and then the fifth location del n2 by del x, and then 0 0 del n3 by del x, 0 0 del n4 by del x, and 0. So like that, del theta y by del y would be 0 0 del n1 by del y, 0 0 del n2 by del y, and like that. No, you can write rest of the things. This would be 0 del n1 by, no, it is derivative of theta x with respect to y, so del n1 by del y, derivative of theta y with respect to x, so del n by del x, 0 del n2 by del y, del n2 by del x, and 0, and so on. No, you can write the other terms. So then now you can say that finally the curvature tensor kappa would be equal to this b into de. This is b and de is a 12 by 1 vector. This is 3 by 12. This vector is a 12 by 1 vector. So now the element is a 4 nodal element. So each node having 3 degrees of freedom. Elemental degrees of freedom are 12. Okay. So I know similarly then you can define gamma. Gamma is equal to del w by del x plus theta x and del w by del y plus theta y. So then you can define now your BS matrix. So this will be into DE. So this would be 2 by 12 and this would be 12 by 1. So D, D I think now you can understand is 12 by 1. D will consist of W1 theta x1 theta y1, W2 theta x2 theta y2, W3 theta x3 theta y3, W4 theta x4 theta y4. So that would be your D. And now similarly, when you are writing this del W by del x plus theta x, so del W derivative is there, so del n1 by del x, and theta x is there without derivative, so here n1 0, del n2 by del x, n2 0, del n3 by del x, n3 0, del n3 by del n4 by del x, del n4 by del x, n4 and 0. So like that, you can write this also. I will write just one element, del n1 by del y 0 n1, del n2 by del y 0 n2, and so on. So you can write the remaining elements. So this would be BS into DE. BS is a 2 by 12 matrix and D is a 12 by 1 vector. So now once you define this, then the element level governing equation, if you look at, I am not derive. I know the steps to derive the element level governing equations are same. So element level governing equation would be the form of the equation is same. Only thing is now we will have this Ke into De will be equal to F external for the element plus F internal. So this is same. Now the when you look at the Ke, the element level stiffness matrix, because B and everything J and all is expressed in terms of zeta and eta. So we carry out this integration in the zeta eta coordinate space. So the area integral over the physical space xy space would be equivalent to integration from -1 to +1, integration from -1 to +1, B transpose into D into B into determinant of the Jacobian matrix into D high D eta. So this will be basically the your element level stiffness matrix. And the similarly the plus, of course, this is the bending part of the stiffness matrix, and plus you will have the contribution from transverse shear strength, so -1 to +1, -1 to +1, and then we have this BS transpose into E into BS into determinant of J into D high D eta. So these two, so this is, if you see, this we call as bending stiffness matrix, and this is the transverse shear stiffness matrix, because this involves in terms of the curvature del theta x by del x, del theta y by del y, and del theta x by del y plus del theta y by del x. So those are the bending terms, so we call it as bending stiffness matrix, and this is in terms of the transverse shear strengths gamma xz and gamma yz, so we call it as transverse shear stiffness matrix. So the contribution to total stiffness matrix from the bending stiffness and from the transverse shear stiffness matrix. So similarly, you could write F external for the element as integration from -1 to +1, integration from -1 to +1, HW transpose into Q into determinant of J into D high D eta. And of course, you have to appropriately carry out the boundary integral. So F internal for the element is those boundary integrals. So boundary integrals can also be written in terms of the area coordinate. So I'm writing that as it is, the integration over boundary HW transpose into Qn plus H theta n transpose into Mn plus H theta s transpose into Mns ds. So this is what now you have these, and I think yeah, I want to stop here. Now if you have any doubts and questions, you can ask. So yeah, are there any doubts and questions? Anybody?
Sir, that Z matrix we wrote, that Z matrix is symmetric, na?
Yeah, it is symmetric.
And sir, if element is incompatible, then there are
Yeah.
actually we did two process to make it compatible. One, we are converting it to natural coordinate, and other, we are considering one extra degree of freedom. Sir, then how we get to know that when to consider which one?
So now you are talking about the classical plate bending element, right?
Yes,
So
sir.
in the classical plate bending element, because the derivatives are also involved. So there, if you see, the primary variables are w, del w by del x, and del w by del y. So if we have a problem where the primary variables are the basic variable and its derivatives, then you will get the compatible element, and that too actually a rectangular element. We get through the additional degree of freedom. But if the primary variables are only without derivatives, like here we have w theta x and theta y, then you can get the compatible element just by formulating the element in the natural coordinate space.
Sir,
So if the
can we
derivatives are
consider?
involved, yeah,
Okay, sir. Hello.
yeah.
Sir, then can we conclude that this conversion to natural coordinate is applicable for all cases?
All cases, yeah, it is applicable to all cases, but if see, the derivatives are also involved. So now the same thing, now if you try to do for the classical plate bending element, where you have primary variables as w del w by del x and del w by del y, w as well as its derivative. So even if you formulate, because we are already talking about the that element with 3 degrees of freedom at each node, w del w by del x and del w by del y I talked about. So that is already a rectangular element in the physical coordinate space, but still it is not compatible. So even if you go to natural coordinate, the same situation will be there. So if, that's what I'm saying. If the primary variable involve derivatives of the basic variable, then it is difficult to achieve the compatibility without introducing additional degrees of freedom. But if no derivatives of the variables are involved as primary variables, then you can get the compatible element by doing the formulation in the natural coordinate space for corresponding arbitrary quadrilateral in physical coordinate space.
Okay, sir. Understood. Thank you.
Yeah. Okay.
Sir, sir, in isoparametric, we are considering four shape functions, but
Yeah.
for the similar case, for the just classical plate bending element, we are considering 12 shape functions.
Yeah, so no, here if you see, although degrees of freedom are same, no, you see w theta x and theta y, so 3 degrees of freedom, and there also we have 3 degrees of freedom, w del w by del x and del w by del y. But you see there, no, del w by del x and del w by del y are derivatives of w. So we have corresponding to w itself, there are 12 degrees of freedom. When you are talking of only 3 degrees of freedom at each node, so corresponding to w there are 12 degrees of freedom. Here in this element, when we are talking of first order shear deformable plate theory, corresponding to w there are only 4 degrees of freedom in the element, w1, w2, w3 and w4. Theta x and theta y are independent, so they are additional 3 degrees, 4 degrees of freedom for theta x, 4 degrees of freedom for theta y. So now for each variable we have only 4 degrees of freedom in the element, so that is why 4 shape functions. They are corresponding to w itself, there are 12 degrees of freedom, so that is why 12 shape functions. Or when we talked about the compatible rectangular element for the classical plate theory, so we had 16 degrees of freedom corresponding to w itself, that is w and its derivatives. So there we had then 16 shape functions. So that is how it is going.
Sir, another question someone asked previously that what will we take the boundary condition for that previous element, that is dw by dx dy.
Acha, you are saying del 2 W, del X, del Y. That's what you are saying. Right? Are you talking about that element where we have del 2 W by del X, del Y
Yes, yes.
also as degree of freedom?
Sir,
So,
what will
see,
be the boundary condition?
boundary condition corresponding to del 2 W by del X, del Y said quite often no, we leave it as unknown. So we write no specify W del W by del X Y, del W by del X and del W by del Y depending on what kind of support we have, and leave the del 2 W by del X, del Y as an unknown. So we do not specify that.
Yes, yes, I remember. Thank you.
Yeah, yeah.
And sir, the shape function we consider for each variable, is it always
Pardon? Say again.
the shape function, a function which we consider, which depends on variable always? No, the
Yeah,
individuals.
yeah. It depends on the variables. Yes, like here we have three independent variables: W, theta x, and theta y. So, and but we are using the same interpolation for all the three variables. So we have same shape functions n1, n2, n3, n4. Now we go for 8 noded element. Then for each variable we'll have 8 degrees of freedom. So there would be 8 shape function for the interpolation of each variable w, theta x, and theta y.
Okay, sir. Okay, thank you.
Yeah. So are there any other question? Anybody? Okay. So if there are no questions, I am stopping. Thank you all for your attention.
Hello.
Yeah.
Sir, actually, in classical plate bending element, if we go for a
Yeah.
quadrilateral element also, then
Yeah.
that will also be incompatible, right?
Yeah. It would be incompatible.
Okay. Okay.
Yeah. See, for the classical plate bending element, you see, you can find lot of the literature papers. So people try to develop different elements to satisfy the compatibility conditions. So there's a lot of literature on these classical plate bending elements. So I have just talked about only two elements, but there are many other elements which are developed for the classical plate bending elements. No, the assembly of three triangles, triangular element, assembly of 12 triangles, quadrilateral element. So those are the different types of elements which are available to satisfy the compatibility condition for classical plate bending elements. So any other question? Anybody? Okay, then I am stopping. Thank you.